When we shoot a projectile on the surface of the Earth, the projectile would follow a curvy path to go up and then down. It turns out that the projectile we shoot is actually on its way to enter an elliptical orbit around the Earth. But unfortunately, the Earth is too big, and it is in the way of this elliptical orbit, so the projectile just crashes to the ground. But if the Earth happens to have all its mass concentrated at the center, still having all its mass, but extremely small in size, and if we somehow still manage to shoot the projectile from that same location, the projectile will be able to enter an orbit around the Earth. If we shoot a projectile at a different speed or a different angle, the projectile would enter a different orbit around the Earth. Of course, in reality, the Earth is not just a small dot. It is big. So when we send the satellite up in orbit without having it crash into the Earth, we have to make the orbit big enough so that it misses the Earth. Well, we also want it to miss the atmosphere, so there is no air resistance to slow the satellite down. For example, if a satellite over here gets a horizontal velocity that equals to the orbit speed we found for circular orbit in the previous lesson, v equals to square root of gm over r, the satellite can enter a circular orbit. If the speed over here is slower than this value, the satellite would get pulled in a little, so the orbit would be elliptical like this. The semi-major axis of this elliptical orbit is smaller than this r, because the slower speed over here means the total mechanical energy is less and therefore a smaller semi-major axis compared to that of the circle. If the speed over here is faster than this value, the satellite would fly outward a little, and the orbit would be elliptical like that. The semi-major axis of that elliptical orbit is bigger than the r, because faster speed means there is more total mechanical energy, and therefore a bigger semi-major axis than that of the circle.